Neural network frameworks. Okay, so far we've been doing everything by hand, which is of course not how we do things. We've been coding the neural networks by hand in Python, which is fine. But when you're doing real work with neural networks, this is too clunky and slow, and we can do it way faster if we use the code that already exists, because people have already encountered this problem before, of course. I want to do fast development of a network. I want to see what works quickly. I don't want to be dinking around with Python code. I want to get right to it. And so various neural network frameworks have been built so that you don't have to worry about everything that's going on underneath. You still know that backpropagation is being used. You know what a dropout layer is. You know what regularization is and the sigmoid function is. You know all these goodies, how they work, but you don't actually have to implement anything anymore, which is where we really want to be in the first place. Now, I dragged you through all of that so that you understand what's going on underneath, but you'll never have to touch it again. Yay! So, okay. Also, Python, of course, is not a high-performance language. Those of you that have taken Python classes with us before, we stress this because it's an interactive language. It goes through an interpreter. It's not high performance. If you want high performance for your code, it needs to be compiled. And so the other advantage of using neural network frameworks is that they, generally speaking, are compiled before they're used so that the training goes much, much faster. Also, they're generally designed to run on GPUs, graphical processor units, which are significantly faster in this particular application, and we'll go over that later on. Okay, so generally speaking, unless you need to hack the framework, which presumably none of you are at that level yet, we'll just use a framework. Okay, the infrastructure is already there. We're going to go over a few of them. Then we're going to talk about keras on Theano, like I talked about at the beginning of class. So Theano is not really actually a neural network framework. Strictly speaking, it's just designed to handle multi-dimensional arrays. It's been around for a little while. It's out of the University of Montreal's machine intelligence group, and it's still being developed. It's written in Python, but it's got a nice NumPy-like syntax. If you're used to it, it'll be pretty familiar. But it generates C code underneath so that it's pretty fast once it gets running. It supports symbolic differentiation, which is good. It speeds things up. And it's been around a while. It's sort of the granddaddy of neural network frameworks. A lot of people used it for a long, long time. It's falling out of favor, mostly because the compilation stage of Theano can be quite long, especially for recurrent neural networks. Theano, I've had one user complaining to me. She said that her neural network on Theano was taking half an hour just to compile. Like, that's ridiculous. That's not cool. So a lot of people have been moving away from it, though, as I said, it's still being actively developed, and they're well aware of the compilation time issues that are with Theano, so hopefully we'll be seeing improvement in that direction. We'll use it today because what we're doing is pretty meager in the grand scheme of things. Okay, TensorFlow, you may have heard of TensorFlow. TensorFlow is Google's neural network framework. It was released in about 1.5 years ago. Second generation framework developed inside Google. It can be quite slow. It's like actually running, it can be quite slow. If you go online and start looking up neural network framework benchmarks, because there are benchmarks out there, given this problem, who runs the fastest. TensorFlow is always on the list because lots of people jumped on the bandwagon because Google came out with it. So it's Google, it must be good. Well, not really. It's getting better. To their credit, it's getting better. It's not the first one I would reach for, but it's worth knowing about that it's Google, so if it's got the power of Google behind it, it will get better. Yes?
Does sklearn not have any neural net stuff?
sklearn has neural network stuff in it. So I actually don't know anything about that. I saw it the other day. So I was poking around on sklearn and discovered that yes, they had neural network stuff in it. I don't know what it's built on top of. I assume it's not the actual engine that's doing the work.
Do you recommend one of these frameworks over
I've never used it, so I can't say, but you do want something that's compiled underneath, whether it's TensorFlow or Theano. Yeah, so it's got APIs for all kinds of languages, and it's growing in popularity. You won't go wrong using TensorFlow necessarily, at least in the long term. Everyone is moving, a lot of people are moving in that direction. Not everyone, to be sure. Lots of people use Caffe. Caffe is for images. If you're using images, you'll find that Caffe is probably still the dominant framework for image analysis. It was developed as a PhD project, so you grad students, you've got a high bar set for you. Develop your own neural network framework in C++. It's currently maintained by the Berkeley Vision Lab. It's written in C++, but it has Python and MATLAB interfaces. So again, it was designed for and is used for image stuff. If you're doing image stuff, Caffe, you won't go wrong using Caffe. Okay, if you're not doing image stuff, don't use Caffe. It's not strong on any other class of neural network. Text, sound, time series, no. Okay, don't use it. It uses HDF5 as its output format, which is kind of handy. But again, you'll see this all the time with image work as sort of the go-to of the image analysis object detection community. Very commonly used. Torch. Torch is old. It's been around since 2002, so it's pretty mature. It's written in Lua. All of you know how to program in Lua, I assume. I never heard of it till I ran into Torch, I'll be honest with you. I joined the club. So that's a downfall. However, Facebook just released PyTorch. I've never used it, but I assume it's some sort of Python interface to Torch, which presumably means it's a little more accessible to those of you that have never used Torch. I've read Torch code. It's not hard to read. Like any other language, you know one language, you know most languages, right? So you just read it. So it's not hard to pick up if you really want to. Again, it's not strictly for neural networks. It is more of a generic matrix linear algebra package. But the thing about Torch that you need to know is that it's rip-roaring fast. This is one of the fastest ones out there. When you go to the benchmarks, it's always on there, and it's always one of the best. Depends on the problem, of course. Certain problems, certain frameworks lend themselves better to others than others. But it's good. It's pretty good, especially on GPUs as well. Okay. Unfortunately, it has limited visualization capabilities. That may be getting better now that PyTorch has been released. You could combine the Lua end of things through PyTorch. You could grab Matplotlib, and maybe things are getting better. I've never actually used it, but there are a lot of heavy hitters behind it. As you can see, Facebook and Twitter and IBM and many others are using it because of its speed. So it's out there. It's worth looking at if you're shopping around for a framework. Though you might have to learn Lua. Keras. Okay, so Keras is just a wrapper, actually. It's written in Python, and it just sits on top of either Theano or TensorFlow. It is a neural network framework, which means all your goodies that you need to build your neural networks are right there. As it says here, it's designed for fast development of networks. You can we're going to do it right now. Just whip out a network in like 5 lines of code, and it'll go. Python 2 and 3, so you're good to go there. And this you need to be aware of. It will try to use TensorFlow on the back end by default. If you don't have TensorFlow, but you do have Theano, you need to modify this file. That if you're on a Linux or a Mac, you have a .keras directory. And there's a keras.json file in there, and change the setting that says TensorFlow to Theano, and it'll just work. Otherwise, when you import keras, in Python, it'll throw an error message because it's going to be looking for TensorFlow and it won't find it, right? If you're on Windows, it's in this directory, user profile, keras.json file. Okay, so check now quickly, or if you're not sure, fire up Python, do import keras, and if it barfs all over the place, then go change your back end. That's a strange sentence. Pardon me. Or you can just set the environment variable. That works too if you're on a Unix-based system, Linux or Unix or Mac.
Is using TensorFlow fine?
You can use it, absolutely. No problems with that. If it's working and that's what you've got, then no problems there. From Kira's point of view, it's seamless. It's the same front end. What's that? I'll ask one of my colleagues to assist you. How do you do that on Windows? I stole this from the Keras webpage. I'll be completely honest with you. Questions now? If you have a problem, raise your hand, and Marcelo or Ramses can probably give you a hand. We'll just quickly get this straightened out. What's up?
I couldn't find that file. So this is a function in file, right? I mean, how?
Not slash. Get rid of the slash.
Right?
Yes, now it'll work.
There's nothing inside it.
Try do import keras first. If you don't have a .keras directory, maybe because you haven't run keras yet, you've installed it but haven't run it. Do import keras, the Python command line. Open up Python, write import keras, and if it fails, which it will, it should set things up. Did you do from Python, not from the bash? So Python, enter, import keras. Now do it. See, it's looking for TensorFlow. So exit, or Control D, works too. Okay, now do that edit, that up arrow, that one.
Yeah.
Yes, if you haven't run it yet, that directory won't exist. You have to try to import it first, have it fail, and then edit it. Theano. So change the TensorFlow to Theano. Theano. Lowercase. All lowercase. Just change that. Save it. Try it again.
Windows, you can open the commands. Is to
Oh no, well go ahead.
press this Windows key.
I'll ask my lovely assistant to.
And CMD will open the command line. And the command line knows this %processing.
Oh, that's how you do that. /.keras.
But this might not have keras yet. But it can go to here. So.
Okay.
It's probably just user / your username code, and that is almost always what it.
So did that work now? Yeah. Import keras. Everyone good? Before we move on, we need this to work. So raise your hand if you need help. Now's your chance. Okay. Okie dokie. So let us, what's next? I think we're going to re-implement. We're going to re-implement. Okay, so the first thing we're going to do with keras is just re-implement the last network we did to study the MNIST data set again. The first thing we have to do, however, is slightly change the format of the data. Okay? Output data needs to be changed to categorical. It wants it in one hot encoding format, which it is not by default. So what you do is you import keras.utils. What's that? No, once the data is reformatted, we'll be good to go. But this will convert it to one hot encoding for us. And we need to do that because Theano wants it in a particular format. So import keras.utils as KU So now I'm just going to change all of my... Have I done this already? I have not. Okay, let's just do this quickly. Take a second, reformat the data. So first I'm going to grab the first 200 data points from the validation data. We didn't use that before. We're going to use it this time. Val out. Out. Okay, and now I'm going to change the format of my training out to categorical. That's what this number 10 means on the end here. It's going to take the data and turn it into a 10-element one-hot encoding. That's what this 10 means. There are 10 outputs. You're going to one-hot encode one of them. And Keras has a function that does that for you. Okay, and then not only are we going to do it to the small data set, which we used last time, we're going to do it to the whole data set. So remember that train out 2 only had 500 data points in it. Now we're going to do it to all 50,000 as well. That's what these last 2 lines are. Okay, so train out. And then val out. And the reason we're doing it this way is because Keras actually has validation stuff built right into it, so we don't have to tweak things quite as much. Take a minute, get that set up. All right, we're getting close. Okay. All right, let's push forward. Okay, so once the data is in the correct format, we can start building our network. Take a second and look at this slide as I explain it. We're going to import a bunch of subsections of Keras. Optimizers, we're going to grab the models, we're going to grab the layers. Subsections, KO, KM, KL. And now we're going to build our model in 4 lines. Ready? First, we say that the model is sequential. Don't worry about what that means. That's what you're always going to use for the time being. Model is equal to km.sequential. Then we're going to add what we call a fully connected layer. That means a layer of the type we've already seen. So we're going to model.add. We're going to add a layer to our network. It's called dense, which is another name for fully connected. I may have forgotten to mention that when we went through the previous slides. The type of layer that we dealt with is called fully connected. It means every neuron's connected to every other neuron that's in adjacent layers. Fully connected layers, also called dense. So we're going to add a fully connected layer. It's going to have 30 nodes. The input dimension is 784, right? And then we're going to say we're going to use the sigmoid function as our function for our neurons. Then we're going to add a second layer, model.add, KL, dense, 10. Activation is sigmoid. I don't need to specify the input dimension because it already knows, right? It follows this layer, so it knows how many inputs it's going to have. You don't have to tell it. You have to tell it on the input layer, obviously, because it doesn't know ahead of time how big the data is going to be or what the dimensionality is going to be of the input data. But after that, you can just keep adding layers and layers and layers and never tell it again. Okay? 10 nodes, activation sigmoid. We're done. That's it. There's your model. Do it. All right. Keras.optimizers as KO. Import keras.models as KM. Import keras.layers as KL. You only have to import them once. Model is km.sequential. Model.add kl.dense. Add a dense layer of 30 neurons. Input dimension 784. Activation is sigmoid. Takes a second. Thinking. Thank you. Model.add kl.dense 10. This will be our output layer. Activation equals sigmoid. And we're done. If you're interested, model.output shape. What's the output shape? 10. Should be for this problem. Good? That was easy. Much easier. Okay, so now what? Now, you have to compile the model. It doesn't actually compile it, I think. I think it does it when you actually get to the fitting stage. But it's called compile. Model.compile. The purpose of the compilation stage. 1, specify the loss function. What loss function we're using? Cost function, right? You have to tell it what kind of cost function to use because we haven't told it yet. 2, we need to tell it how we're going to optimize this thing. Gradient descent is what we've used before. We're going to use a slightly different optimizer this time. That's what that ko.sgd is. Stands for stochastic gradient descent. We'll talk about that in just a minute, okay? Once you've compiled it, you run the fit. Fit equals model.fit. Put the data in. Number of epochs, we'll talk about what that means in a minute. Batch size, again, we'll talk about that in a second. Validation data, and then verbose if you want to see all the output as it calculates things. And then it's going to march along, boom, 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 boom. And then there's your accuracy on the training data. And here's your accuracy on the validation data. Okay, where am I? Over here. Let's hide over here. Okay, model.compile. Optimizer is equal to ko.sgd. LR equals 1. We'll talk about what that means in just a second. Metrics equals accuracy, which is just telling it what I want it to print out as it goes. Loss is equal to mean squared error, our old friend, the quadratic error. Okay, that's why I say it probably didn't compile it there because that was too fast. Fit equals model.fit train in to train out to epochs equals 100, batch size 10, validation data, val in 2, val out 2, verbose because I like to see what's going on. Boom. And now it's getting compiled, I think. That's because it takes a second. But you'll notice how fast it runs. Is everyone done? If it's compiled, you're done. Watch. Oh, well, never mind. This problem's trivial because it's done. 98.4, validation 87.5. You can see the overfitting problem again, right? There it is. 98% on the training data, 87.5% on the validation data. We'll come back to that problem in a second. Did it work? Did it not work? How about that? It didn't work?
No, I had the phone. I didn't
Boo. Should have worked.
put the import of the
The data?
when I put it in ASCII code.
That's bad error. I apologize for that. I didn't actually test it.
What again is the meaning of the 100 and the 10 there?
I'll tell you in 1 second. I'll tell you 1 second. Other questions? We're good to move on, or? Just 1 second. As soon as it compiles, it's going to shoot right through it. It'll be really fast. Okay. And that's it. Like, that's how hard it is to put together a neural network with keras. Once your data is in the right format, you're good to go. Let's talk about that, the epochs, the batch size, and the optimizer. So I taught you originally gradient descent. Gradient descent is an algorithm that nobody uses. And the reason nobody uses it is because it is slow. Oh my goodness, is it slow? And on full data sets. That's why we only used 500 data points to train it in the first place. Because if I had put in 1,000 or goodness gracious, 10,000, we would still be waiting for it to finish because it's just slow. So there's an alternative algorithm called stochastic gradient descent. And the difference is, instead of training on the entire data set for every iteration, we're going to train on a little batch of the data. And that's what the batch size variable means. It says take 10 of the data points only. Take 10 of them, update the parameters on just those 10. Then do it again with a different set of 10. Take them out each time. Don't repeat. Keep pulling out batches of 10, updating the parameters until you've done the entire data set. That's 1 epoch. Then you do that 100 times. That's 100 epochs. That's what those mean. Okay? Nobody uses gradient descent. The only reason I use gradient descent is because it's a lot easier to code, and so that's why I just did it. Okay? Well, no one uses it, and you won't either, ever again. Stochastic gradient descent. Okay? Way, way faster. Okay? There are disadvantages to gradient descent as a general rule. We'll talk a little bit about those. But if the first algorithm you reach for to optimize your cost function, to minimize your cost function, is stochastic gradient descent, no one's going to fault you for that. Okay, it's a good starting point. You may try others, and we'll talk about some of the others, but it's where everybody starts. That's why it was so fast, right? Once it compiled, boom, it's done, because there's only 500 data points.
For batch of data, will the weight correspond to all data sets?
It's a slightly different algorithm, so you will get a slightly different answer. Yes. Does that answer your question? Or other questions? I think we covered this already, but I'm going to mention it one more time. Okay? When we did the compilation of the model, we had to specify the loss function. We had to specify the optimization algorithm. The only reason I actually had to pull it in was because I wanted to specify the learning rate, LR. Where is that? LR equals 1. That's your eta. Remember eta, the step size of your gradient descent? That's what that specifies there. It stands for learning rate in this case, and the reason it's different is because the size of it is a strong function of the batch size, right? So as you tweak, this is another knob you get to turn. Batch size, number of epochs. You can also just do the default parameters, whatever they are for SGD, and we'll do that for the rest of this class. Okay. As I said, the only reason I used regular gradient descent was because it's easier to code. That's the only reason. We won't do it again. Okay. So we had to specify the loss function, which was our quadratic loss. The optimization using the optimizer flag. If you just put the string SGD in, it'll use the default values for SGD, stochastic gradient descent. Oh, there it is. Yeah, I specified it explicitly so I could specify the value of eta. Okay, and the metrics argument is optional, but if you want to see how well it's doing as a function of the number of epochs, you have to specify all that stuff. Questions? Okay. Now, test data. Have you done the test data yet? This is how you do it. You have to convert it to categorical again because we haven't done that yet. Model.evaluate, test in, test out. 87% on this slide. Still not very good. Let me try it myself as I get out of the way. Test out 2 is KU to categorical. Test out 2, 10, and then model.evaluate, test in, 2, test out, 2. 86. 86, which is pretty close to the validation numbers, if I remember. 87. Oh no, what were my validation numbers? I'm in the wrong slide. Validation numbers for me was 87. Is that sort of what people got? The test score is about the same as the validation score. We're seeing the overfitting problem again, right? Got a really good score on the training data. Validation data and the testing data, not so good. The first rule that I gave you for fixing overfitting was more data. You saw how fast that ran. So we can use more data. There are a couple of other options we can use, and we're going to explore some of them here. Let's go down a quick list. 1, use more data. We said that already. We have 50,000 data points. Stochastic gradient descent can handle 50,000 data points, at least in a reasonable amount of time. 1, we can change the activation function. We don't have to use sigmoid. There are others out there. 2, change the cost function. We don't have to use quadratic cost. Or the optimization algorithm can be changed. We can also change the way things are initialized. We're not going to talk about that. That's an entire branch of neural network science in itself. And we can also add regularization if we want to. Turns out probably that's not necessary for this particular data set, just because there are so many data points. But it is worth playing with, and it is built into keras right there. Okay? And then there's finally, we can abandon the entire approach and try something else, and we'll do that too in the last section of the class. Okay, let's go over some of the things we can improve before we totally abandon everything we've done already. This is starting to sound kind of ad hoc. Right? This didn't work, try this. That didn't work, throw something else at it. And the answer to Danny's question is that's what people do in this field. They try it, they try something else, they try something else, and see what works. There are certain classes of activation functions instead of sigmoid is never used actually in the field very much. There are other cost functions, we'll go over some of them. No one uses mean squared error. I used it just because, again, it's easy to demonstrate how it works and why we use it. But there's a lot of art to this, and you'll find that if you start reading a lot of the literature, you will see this network uses this network uses that, this person tried this over here. There's a lot of that in the field. If it seems like I don't know what I'm talking about, it's because nobody knows what they're talking about, and I'm up to date. So that's just the way it is. So don't feel bad if you don't know how to proceed and you just start throwing stuff at the wall, seeing what's going to stick, because that's the nature of this beast, okay? number of nodes, trial and error, activation functions, like you've seen how many free parameters we've already seen, right? Epoch, batch size, eta, number of nodes, number of layers. It goes on and on. Okay, so practice and talk to your colleagues. Read the literature. If you go down this road, other people have already been where you're going probably, so do some reading, see what's out there. Okay, your particular subfield probably has ways of doing things, so start there. That being said, it's good to review some of the functions that are out there. First one, like I said, no one uses sigmoid at all, and there are good reasons to not use it. And we'll talk, well, we may or may not talk about them, but here's one that you will see, RLU, rectifier linear units. This is what it looks like, this yellow line here. It's 0, 0, 0, and then goes straight up. That's it. Okay, it's that simple. Sometimes you'll see softmax, which is the functional, soft plus, excuse me, which is the functional form. It's that blue line there, very similar to to the rectifier linear unit. Okay. The bad part about this is that the function's unbounded, so potentially could blow up on you, and your network will not be happy when that happens. The good part about it is that there's a problem. We're not going to talk about it. There's too much material to cover, but there's a problem called the vanishing gradient problem, which will cause your network to stop training. You can see it in your head, right? If my derivatives go to 0, my network's not going to train, right? I need my DC, partial of C with respect to everything, to be non-zero. It has to be something. If it goes to 0, then my network stops training and I just sit there and I can't get any improvement. That's called the vanishing gradient problem. This does not suffer from it. So it's worth exploring. Questions? Tanage also shows up a lot. Okay? You know what it is, right? It goes from -1 to +1. Okay? It's got strong gradients, which is what we want, right? Strong gradients push our weights and biases in the direction they need to go. Okay? It does not suffer from the vanishing gradient problem. It also, because it's anti-symmetric about 0, it's very good at pushing the weights in whatever direction they have to go. Sometimes you can run into problems with, I can push stuff positive, but I can't push stuff negative because of the nature of my activation function. This function does not suffer from that problem. So you will see Tanage used as your activation often. Good? Softmax. This function is used on the output layer. And all it does is not all, but it takes the output and just raises it to the exponential, but it normalizes it by all the other values that there are there. So if I have 10 output nodes, the jth output node will be e to the zj, divided by the outputs of all the other nodes to normalize it. The reason for doing this is because, one, it keeps your outputs between 0 and 1, and it converts all of your outputs to a probability, or something that can be interpreted as a probability. And if you need to do that, this is a good function to use. You will see this almost all the time on the output layer. In particular, if you'll see some neural network papers where they've analyzed an image and the network has put a box around a cat, and then it says cat 0.98. 98% chance that this is a cat. And then there's a dog, and here's your bicycle. Stuff like that. That's where these numbers are coming from the output of a softmax function. Questions? Okay, so those are our activation functions we can play with. We can also play with the cost function. The main cost function you will see that is not quadratic is called crossentropy. This is the function. It looks gross. It didn't come from nowhere, though. what happens is when you take the derivative of this function, the derivative is the value minus the distance that it needs to go. It's a linearly separated from the goal, if you will. That was very poorly exposed. Let it be sufficient to say it's a really good cost function. I recommend using it. A has to be between 0 and 1. The output of the network has to be between 0 and 1 for this function to work. So you'll always see this coupled with the softmax function we just saw on the last slide. Okay, in this particular example, V is 0.5. Here's your quadratic. Here's what the cross entropy looks like. The gradients are much stronger, as you can see. Yes, sir.
This function looks very different from the other ones insofar as it would go like say to minus 1 to 1 or something.
Yes, this is the cost function, this is a cost function, not the activation. Right. So, different class of function. Just did a change there. Other questions? Okay. Anything else? Optimization algorithms, the other thing you can play with. Stochastic, I'm going to go over these names. Don't worry about what they are necessarily. When you're starting to develop your own networks and you run into a problem and you can say, oh, Eric said something about other optimization algorithms, go grab the slides, pull up this slide, look up these acronyms, figure out what they are, okay? Basically, gradient descent has a whole bunch of variations on it. Stochastic gradient descent, I should say. Don't use gradient descent. Stochastic gradient descent, RMS prop is popular. Atom just came out. It seems to actually do wonders on some of the work I've been doing. Newton's method has been used because it uses second derivatives, and it's got a few variations that have been used for recurrent neural networks. Conjugate gradient has also been out there. Dantley squares only works on the squared cost function, so don't use it on cross entropy. Again, if you get stuck, and you will find this, you'll set up your network, you'll say fit, and it'll march up, it'll hit 73%, and it'll just sit there for thousands of epochs and not do anything. And you're like, oh, geez, 73%, I can't. Yeah, I'm looking at you. 73% is not going to get, I can't publish that. Okay, so you got to start tweaking things, right? Change your functions, change your cost function, change your activations, change your optimization routine, find a way to kick it out of its rut. Okay? Questions? Okay. We're going to redo the network again. But the only difference now, well, not the only difference, we're going to change a few things. First, we're going to use Tanage as our first activation function. For our 30 nodes, we're going to use softmax. For our output, we're going to use cross entropy. Categorical cross entropy is what it's called in keras. Cross entropy as our cost function. We're going to just use the regular stochastic gradient descent as our optimizer. Optimizer equals SGD. And we're going to use all 50,000 points this time. Do it. Yep, where am I? Get off the screen though, Eric. All right, model 2. Model 2. KM dot sequential. Model 2. Add. Model 2. Okay, so it's 30 nodes. You still have to specify the input dimension, but the activation function is not sigmoid. Now we'll use Tanage instead. Tanage. Boom. Okay. Model dot add. Where is that? Okay. Model 2 dot add. Dense 10. Activation is now softmax on the second layer, the output layer. Softmax. Okay. model.compile, model 2. Optimizer is just SGD. And the loss function is now categorical cross-entropy. And now, the full data set, because I'm using SGD, I can do that. I guess I switched it to a batch size of 20. You can experiment with what batch size you want. Validation data. $50,000 data points goes a lot faster than you might think. Boom, boom, boom. Not bad. How are we doing? You'll notice right away, once you get yours running, that the validation data accuracy and the training data accuracy are pretty close to each other. Much, much better than before. And I am only using a single core on my desktop when I do this, just for reference. Theano can use many cores, yes. How's it going? Is it working? Is it running? Is it fast-ish? Fast enough? I mean, it's not as fast as 500 data points, obviously, but what are we at? 97, 98, 99, 100, 98.76 for me, 96.4. Not bad. Not bad. Is that more or less what people are seeing? Something like that? You specified it here, right? Train in, train out. Is that?
Before, wasn't it saying the same thing? Or maybe
No, it said train in 2 and train out 2. Those were the restricted data sets we built, the small ones. Other questions? Does it work? Tamok? Yeah, all right, good. All right. If it worked, then it's time to check the test data and see how we really did, because the test data is where it's at, right? It doesn't do you good to do well on the validation data. Oh, I haven't converted this yet to categorical, so we'll do that quickly. To categorical, test out 10, and then model 2.evaluate, test in, test out, and the winner is, boo, what's, uh-oh. I must have, hold on. Pardon me a moment while I find my error. When I must have called it the wrong thing when I test int. No, my problem is that I don't know how to spell. I had a feeling it was that. I've done that before. Hold on. So let's do that again. Test int. 96.5. 96.5. Not bad. Did everyone get something like that? 96-ish? $96. Not bad. Not bad for a few hours of training. Yes, sir.
Let's look at the syntax for the optimizer on this model versus this one, where before you would use the optimizer
Right.
Whereas if we just say optimizer.
I use the default. I'll be honest, I can't remember what the default parameters are. You can go to keras and pull them up. There are a bunch of flags you can specify for the stochastic gradient descent. In particular, there are modifications to the algorithm that involve momentum and how quickly the value of the step size drops. So one modification to the algorithm is to march it along and then start making it smaller and smaller and smaller, since in theory you should be getting closer to the answer and you don't want to take such big steps anymore because you're just going to shoot right past the minimum. But I don't remember what the default values are. But you can use the default to start, then you can start playing with it. And if it doesn't improve things, then save yourself the sweat, right? No problem, no problem. Okay. Are we good here? Everyone's okay? Everyone's worn out? That's good. All right, success then. All right, so that's about the best we can do with this approach. We can push this even further, though. Like I said, the goal was to do better than 98%. So far, we've only done 96-ish, 96.5%. We can do better than that. State of the art is over 99. We're not going to do state of the art today. 98 we'll have to do. Let's talk about a few things, and then we can decide what to do after that. Okay, so there's not enough time to cover every single possible knob you could tweak. Here are a few more tweakable knobs. Okay, first, pre-processing the data. And this particular data set is pretty good. It's already been centered and normalized, so you don't have to do that. But if you've got a highly dimensional set of data, which has degrees of freedom which are unnecessary, try to get rid of them. This is true of all machine learning algorithms, right? You want to rip out any extra information that's not adding anything to your problem, because the algorithms always perform much better and much faster if you don't have extra degrees of freedom that aren't needed, right? If there's no information in that dimension, get it out of there, okay? So pre-process your data to clean it up. Initializing those weights and biases, there's an art to it. Just randomly picking numbers out of a hat is not actually the best way to do it. There are better ways. They don't necessarily lead to a better answer, but they lead to a faster answer. You will converge much faster if your random numbers are of a particular form. We're not going to go over that, but if you're interested in delving into this topic, if you're going to start using neural networks for your research, be aware of that particular subclass of problems, the initialization of the biases and weights. As we said, there are many activation functions. Play with them. Certain fields lean towards certain activation functions over others. So know what your field is using. And again, there are more cost functions. Training failures, I talked a little bit about this. One of them is the vanishing gradient problem, right? Your derivatives go to 0 and your network just sits there looking at you going, why me? I can't improve because I've got nothing to work with. So usually the solution to that is to change your activation function, but another technique for fixing that is to use dropout. That will help also. Okay, dropout's built into keras. We're not going to use it, but it's just another model.add dropout layer, whatever. Find the syntax. It's there. It's trivial. There's also the exploding gradient problem, which I've never experienced myself, but as I understand is very embarrassing. So be aware of the classes of failures of your networks. Okay, where are we? What next? Okay, so now the question is, what do we want to do? Do we want to take another break, or do we want to push forward? We've got another hour's worth of material-ish, not quite an hour. What do you guys think? 10 minutes? Stretch your legs? Don't care, gonna go to sleep anyway. Push forward. Okay, let's do it then. Okay, as you might have noticed, we took a two-dimensional image and made it one-dimensional. We threw away all the spatial information that was there. Should have been like warning flags going off, like, what are you doing? That's you threw away information. If we're going to do better, maybe we could, like use the information that's there, right? Okay, so there are a couple of things we're going to do. First of all, imagine what a typical problem might look like. I might be actually getting ahead of myself here, okay? We used black and white. It's more typical, like 28 by 28 pixels is pretty small, right? Something 200 by 200 is still pretty small. With 3 colors, though, that's 120,000 input parameters. You can start to see how things are going to spin out of control pretty quickly if you have to analyze 3, 4, 500 by 500 pixel images, right? And those aren't big by any means. Okay, so we're going to need something that's more efficient. An approach that we could look at is to use the spatial information, right? This is a 28 by 28 image. It's not a 784 by 1 image. Okay, so how can we redesign things to account for the spatial information? And the answer is what's called a convolution layer. Okay, we're going to completely change our approach. Well, not completely. We're going to change our approach. Instead of using 1D information, we're going to put the image back to 2D. This is 28 by 28. Okay, here's our input layer. We have, in this case, 20 by 20 nodes, 400 nodes. But each node is not going to take all 784 inputs. Instead, this node here in the corner is going to take input just from this 5 by 5 grid. This node over here is taking information only from this 5 by 5 grid. This one over here, that 5 by 5 grid, and so forth and so on. Okay? This is called a feature map. We're going to preserve the spatial information that we were given by reducing the amount of image we actually look at with each neuron. You with me? Because it's got what's called a stride of 1. Okay, so 5 by 5. How many steps do I take before I do another 5 by 5? I've stepped 1. Step of 1. You can step, it's called the stride. You can stride as many as you want, and we'll stride a different number in just a minute. If you stride by 1, then you only get a 20 by 20. If I stride by 2, you'll get a smaller number of nodes. You understand? It's the amount of steps I take.
Do you have shared?
Yes, they have shared input. They overlap, right? This node gets this 5 by 5, these 25. This node gets this 25. One pixel over. You can stride as many pixels as you want. Okay? Now, notes about feature maps. There's a very, very important flag I need to draw your attention to. It's this third bullet. Okay? The weights and biases are shared by all the neurons. There's only one set of weights and biases for the whole thing. All 400 neurons are sharing the same set of weights and biases. They only take the input from those 25, their particular 25, right? 5 by 5 grid. But we're going to share the neurons across everybody. Why do we do that? We do that because what we want to do is train the feature map to recognize a single feature in that image. Just one sort of shape or edge or whatever. Okay, that's why we only use one set of weights and biases. So now my feature map only has 26 parameters, right? 25 inputs plus a bias. Okay? Now, that's not going to get you very far because my digits all have different shapes. So instead of just having one feature map, we can have an arbitrary number of feature maps. So that this feature map will learn this particular shape, this feature map will learn this particular shape, this feature map learns a different one. These are also called filters. You also see them called kernels as well. So what actually ends up happening with our first layer is it looks like this. Here's my input layer, and then I have an arbitrary number of feature maps right after it. This one, the orange set, has one set of weights and biases. Blue has another set of weights and biases. Red has another set of weights and biases. They share them, but because the input is only collecting on specific spots, it allows the network to learn shapes. And you can actually look at pictures of what these look like after you train them. You can say, oh yeah, it's just learning this shape, and this has got this weird thing, and there are all these different shapes and features that it learns. Nope, you just specify, I want a kernel size of 5 by 5. I specify what my stride is, and default is 1. And then I specify how many of these I want.
That's it?
That's it.
So how do not they're the same?
Because they're initialized randomly, and that's just the way it works.
Same name, they're the same name?
It won't.
They won't?
No. It's the nature of the beast. They don't learn the same thing. No, and because this is not the only layer, there's more layers after this, which will help force them not to do that. You'll see that in just a second, yes?
So just to add on that, can you also miss features if you're randomizing initialization?
Unlikely. You could miss features if you don't have enough feature maps. But I would expect that you'll capture everything you need to if you have enough of them. Other questions? After your feature maps is another layer that's generally associated with your feature maps. It's called a pooling layer. One of the purposes of the feature map is to reduce the number of parameters because, like I said, if you've got 120,000 inputs, you don't want that many weights. 25 by 25 times 3 for each color is plenty. So if we want to reduce the amount of information we have, we can use what's called a pooling layer. Pooling layers don't actually have an activation function in them. All it does is reduce the amount of data. Generally speaking, what have we got? Oh, I'm just getting ahead of myself. So here's an example of a 2 by 2 pooling to a single neuron with a stride of 2 this time instead of just 1. So here we did a block of 2, block of 2, block of 2, like this. So now what we've done is we've stuck a function into our network, a function that acts on the output of this layer, but it doesn't actually have any parameters in it, so there's nothing to fit. All it's doing is reducing the amount of information we have. You with me?
So how we map for
You pick, there's no randomization. It's a function. So in this particular, the most common one you will see is called the max pooling, which means take those 4, just grab the max, whatever one's biggest. The purpose, again, is to reduce the size of the data so that in layers that come after this, it'll become easier to fit them. The reduction in the data also helps with overfitting. Okay, pooling layers use other functions. As I said, usually max is your most typical function. As I said, it takes the maximum value. There are others out there. Average pooling is sometimes seen, L2 norm pooling. I can't speak to one advantage over another. The purpose of it is just to reduce the amount of data so that there are fewer parameters to fit, because we're going to add another layer right after that. And so the amount of input is reduced before it goes to the next layer. Okay? Good? Okay. Yes? I'll show you. Okay, I'll show you. Okay. We're going to do it one more time. This time I need you to reload the data, but use the MNIST loader load data 2D. So this is going to give you the data in its 2D format instead of 1D. And if you look at the shape, you'll see it's 50,000 by 28 by 28 by 1. The 1 is there because it's an image and it needs to have, Theano is expecting a 3D image to come, so you need to put 1 on the end to tell it, no, this is actually just a 1D, one grayscale. Okay, that's why that's there. Okay. And then let's convert it back to 10 again, and then we'll be ready to go. Actually, you don't have to do this step, now that I think about it, because it's the same data as before. Just do the ones up top, the one up top. Let's do that quickly. Okay, train in. Train out. In fact, I can just up arrow, go change this to 2D, and I'll be good to go. I put this here just as a note. Where that channel, that third dimension goes in your image depends on how you've set Theano up or Tensorflow up. Generally speaking, it's at the end. If you're not sure, import the back end and then do image data format, and it'll say channels last or channels first. Channels last means that third dimension goes at the end, not at the beginning. By default, I think everything's consistent, so it should be okay. Train out. That shape, do we have to change it? Oh, we do have to change it. Oh, I lied. Okay, do it anyway. I'm sorry. Put that back. Do you have to change the dimensionality? But the code should already be in your, if you're using IPython, it should already be there. Okay. It's load MNIST 2D. Boo, I'm sorry. I knew there'd be a typo in the slides. It's just a matter of time to find it. Load MNIST 2D. The first time was load MNIST 1D. I apologize. Forgive me. Okay, got your data. It's 50,000 data points. It's 2D now. So let's build our network. No, they're still typing. Okay. So to answer your question, this is what we're going to do. Okay, here's our input layer, 28 by 28. Then we're going to have convolution layer, some number of layers. I think I picked 20, but we'll see what it is in a minute. Okay, then we're going to have a max pooling layer. Then we're going to go to our old friend, the regular fully connected layer. Then we're going to go to the output layer. 4 layers. 3 hidden layers. Okay? If you're a little confused as to the path of an individual piece of data, this is how it works. 5 by 5 to there, boom, it hits the whole thing, right? This is fully connected, so it's going to hit all of them. These all have their own weights and biases now, unlike these guys, which share them. Green, yellow, red. These guys have all their own. And then to the output layer, of course, these all go to all the output neurons, but I drew that and I couldn't read it anymore. And then it comes out. Okay? That's the path. But as you might imagine, keras makes it trivial. It's 5 lines. Right? Here we go. Sequential, our old friend. Then the KL is, the model is conv2D. That's the layer for your convolution layer. Okay? Add conv2D. Number of feature maps is 20. Kernel size is 5 by 5. Stride is 1. You don't have to put that if you don't want to. It's optional. Input shape you must specify, obviously. 28 by 28 by 1. And in this case, we're going to use the RELU. I've already forgotten what it's called. Activation function. Then we're going to throw in a max pooling layer. Pool size 2 by 2, stride of 2. Then we're going to flatten it, which means make it 1D. Then we add our 100 nodes, because we're going to be awesome. Add 100 nodes with a Tanage function. Then we're going to add our final output layer with a soft max activation, and then we're done. All right, here we go. This is going to be awesome. Or something. All right, Model 3. Model 3 is km.sequential. Here we go. Model 3.add kl.conv2d. 20 feature maps, kernel size of 5 by 5. I'm going to skip the strides because it is optional. That's the default value, is 1 by 1. Input shape 28 by 28 by 1. Activation is equal to RELU. Enter. Nope, what did I do wrong? Oh, thank you. Marcelo's there. Beautiful. Okay, model 3 dot add. I'm going to add my max pooling layer. 2D. Pool size of 2 by 2. And a strides of 2 by 2. Now I'm going to Thank you. I'm going to flatten it so that it knows that I'm going to feed this to a fully connected layer. Flatten. Okay, then I'm going to add my fully connected layer, also called dense. 100 nodes, activation of Tanage. And then I'm going to add the output layer. kl.dense. 79 and 80. This is, give me 1 second. Let's just finish this. Okay, model is built. The difference is that it's the second last layer. So that's this layer and that's this layer, the output layer. So this one will have 100 nodes. This is not 100. I couldn't. Right, because it was 2D. Now I flatten it so it becomes 1D. So keras knows how to feed it into this layer. And then this has a Tanage activation function. This one only has 10, and it has a softmax activation function. That's the only difference. Everyone with me? All right. So then, okay, if you want to see what this actually looks like, you can do the .summary command. This is kind of good to see. So dot summary here, so it just gives you the output, but it gives you the various layers you've put in so you can see the status of things, right? So the output went from 48 to 28 by 28, excuse me, to 24 by 24 with 20 layers. There are only 520 parameters in there, so that's encouraging. Then with max pooling, we dropped it down again to 12 by 12, also 20, but there were no parameters in that layer. We flattened it, that's not got no parameters in it. Then we put in our big boy, 100 nodes. This one's got lots of parameters in it, 288,000. And then finally the output layer, 10, that's got 1,010 parameters for a grand total of 289,630 free parameters. No problem. Here we go. Okay, so compile it. Categorical cross-entropy, regular stochastic gradient descent, and then run it on the full training data set. 30 epochs only, because we all have to go home, and batch size of 20, validation data, and everything else is the same. Okay, this will take a minute, but get it fired up, and let's see what we got. Model 3 dot compile. Loss is the categorical cross entropy again. Oh, I've got it here. Awesome. Categorical cross entropy. And then fit is model 3. No. Train in. Train out. Epochs. We don't need to do 100 this time. 30 is plenty. Batch size is 20. Validation data. Validation data. Almost. Data is val in. Val out. Verbose equals 2. Okay, here we go. Takes a minute to compile. Okay, there's a lot going on in there, as you saw. So now, okay, here we go. Another nice thing with verbose equals 2 is that it gives you the amount of time that it takes per epoch, right? 23 seconds, that's not too bad. This is, of course, a rather modest network, as networks go. We're already at 88% though, that's pretty cool. Is it working? It's running? Okay. 23 seconds, okay, how long is this going to take? 10 is 230, that's a few minutes. 10 minutes, all right. What's that? Let's do a break. Oh, I have to go to the bathroom. I'm going to the bathroom. I'm going to turn this off. Though. Give yourselves, let it run, give yourselves a few minutes, stretch your legs, and we'll come back in, what time is it? Quarter two. Okay, on the slide I got 98.87 on the testing data. That's 113 out of 10,000. Not bad, right? Not bad at all. How am I doing here? Did I finish yet? I'm very close. Here we go. Let's do it. I'm ready. And what you'll find, if you improve it even farther, or even just pull some of those 113, dig into the data set, pull them up, plot them, see what they look like, and you'll probably convince yourself that, you know what, the network did an okay job, right? He thinks that's a 6, but it's actually a 0. Yeah, I can see that, you know, or someone made a 2 that's totally not a 2, and I don't know what he was thinking when he drew that number, so that one's correct. And, you know, you can understand where the code is coming from when you get to this level of accuracy, right? So we'll do my test in just a second. You can improve this even farther by adding another convolution layer and max pooling layer after the first pair, but before the fully connected layer. And of course, expanding the data set, or adding dropout, or adding regularization. Okay, these will all improve things past the 98 point whatever you got. Did anyone get less than 98 on their test? Take that as a no. Okay. Okay, so you can push this farther. As I said, state of the art is 99.6% correct. And those 30 or whatever it is that are wrong, you can just say, whoever wrote the digits wrong. Like it's just, it's not, I've seen the digits. They're not, there's nothing wrong with those digits. The computer classified them just fine. What's going on here? Come on. Oh, there it is. Okay, here we go. 99.88. Oh my goodness. All right, model.evaluate. Test in, test out, not to. Test int, if I remember correctly. And it's not model, that's the, no, it's model 3, isn't it? Model 3. $98.95. Not bad. Not bad. Again, initialization matters here, okay, but not bad. Okay, questions? That's all I have to say about the MNIST data set. What more could I say? We're just going to talk a little bit now about neural networks in general to finish things off, because that's enough hands-on and we're all pretty tired. So let's just talk a little bit about a few notes. We only have 4 more slides, so it's okay. A few notes about the convolution network. Okay, so that's called a convolution network. You'll see it called CNN in the literature, convolution neural network. That's what it's talking about. It's obviously, this is only for image analysis, right? This is not for other classes of data. It's got to be 2D. We're 2D with multiple channels, right? Red, green, blue. Often you'll see more than one convolution layer, pooling layer together. They're usually together, and often you'll see multiple sets of them together. Again, one layer is learning features, and then the next layer is making more intelligent decisions about what was learned in the first layer, and then again, and so on. And then usually people finish things off with a fully connected layer. Not always. Sometimes they'll just flatten it and send it to the output. That works too. Okay, usually the output layer is always a fully connected layer, but in practice, all manner of combinations of layers are coming up. Again, trial and error. If you're not sure, throw more nodes at it. If you're not sure, throw another layer in and see what works. Okay? GPUs. Okay, I ran this problem with 50 and 250,000 on a CPU-only system. We saw that the first time took 21 minutes. I wasn't working on the machine that I was just running on now. 21 minutes. The epoch took 41 seconds. On a CPU GPU, 2 minutes and 4 seconds. So you can see that no contest, right? A factor of 10 in time speed up for that problem. For the 50,000, 250,000 was not quite as big an improvement, but nonetheless, if you're going to be training big data sets with hefty nodes, networks, consider finding yourself a GPU node to run on. Okay, Compute Canada just had a whole bunch of, or is about to unleash a whole bunch of them out in BC and in Waterloo on the 2 new machines that Compute Canada is commissioning as we speak. They should be out in the next few weeks. They all have GPU nodes on them. So you should, in theory, be able to run on those nodes, use the GPU-CPU combination, and get considerable speed up. What sort of speed ups were you seeing? We had some test nodes here at SciNet that were being used. Chris, you were using them.
Yeah, it was like fairly insane. Like untrainable on the laptop, a couple hours on the desktop. Probably not
Right, exactly. That's the sort of scale we're talking about, all right? Get on a GPU node if you've got a heavy problem, okay? The multi-GPU functionality, this note at the end here is important, so I got to get that out of there. The multi-GPU functionality is available on Theano and Tensorflow, but not with keras on top of Theano yet. Okay, this functionality is brand new to Theano. The ability to use more than one GPU simultaneously. The new nodes out in BC and Waterloo will have multiple GPUs on them. Some of them will anyway. And in theory, you can use multiple simultaneously. That functionality is not built into keras yet. They're working on it. It is on the TensorFlow side, though. Okay, so if you're running keras on TensorFlow, you can use multiple GPUs. So be aware of that. Questions? Does anyone not know what a GPU is? I probably should have started with that. Graphical processor unit. It's the graphics cards. People discovered at some point that you can take the graphics cards that the gamers were using with their desktops and use them for computation because they do matrix algebra really, really well. That's a GPU. Okay, deep learning. What is deep learning? This is like the super hot topic. All these startups are jumping out of everywhere about deep learning. It's just a neural network with more than 2 layers. That's all it is, guys. Seriously, that's all that deep learning means. Technically speaking, the last thing we did was deep learning, strictly speaking. You will find state-of-the-art networks have dozens of layers, and they take days to train because it's just slow. When you've got that many layers, it just takes a long time to do anything. Okay? Up until the mid-2000s, we were just doing shallow networks, which means 1 hidden layer, maybe 2 hidden layers, okay? But we discovered that it was practical to train networks on a large number of hidden layers. 1, because we discovered GPUs were really good at this, and 2, we discovered, with the help of the internet, that you can get gobs and gobs of huge data sets that make training these things practical, right? If you have a situation where you've got so many free parameters that doesn't matter how big your data set is, you can't train it, then you're not going to get anywhere. But again, we now have data sets with tens of thousands or hundreds of thousands of samples in them. And so these, well, you saw, we had 200 and whatever thousand parameters in that last model, and 50,000 parameters was okay, or data points was okay, right? So sufficient computing power and accessible to huge data sets made this deep learning field practical and, well, something that everyone's working on, right? But that's all it is. It's just deep, many, many, many layers. People get disappointed when I say that. They're like, what? That's it? Yeah, that's it, guys. That's it. Okay, other neural networks. We've only talked about 1, 2, really. Fully connected and convolution. Those are the only 2 sort of classes of networks we've talked about. There are lots of others. Recurrent neural networks are very hot right now. That means networks that feed back onto themselves. Take the output, feed it back in as input. Here's a rough diagram of what sort of happens. You stuff stuff in, these are your layers, and you just take the data out, but you feed it forward, and the data from itself is fed into itself. And the purpose of doing that is to have memory. You want your network to remember something, you got to give that information back to the network, right? And that's what these networks do. Okay? Hard to train, long to train, but very, very powerful. This is any sort of data that is sequential in nature needs to use this sort of network, right? The data we've been using so far is, here's your data, all of it at once, boom, and you're done, right? But if I'm doing text analysis or language processing or anything where things come in a sequence, and I need to analyze what's here, but I need to remember what came over there, then I need some sort of network that can remember things. And so that's what recurrent neural networks are used for, okay, RNNs. You'll see them all over the place, especially the class called LSTMs, long short-term memory networks. Again, I don't name them. Modular neural networks, you can have glued together networks together that end up feeding each other. The output of one network becomes the input to another. Self-organizing maps, somebody asked about self-organizing networks that grow and change depending on input from itself. Self-organizing maps, that's the name you're looking for. They design their own architecture as they go. Weird. I've never used them. I just looked them up to find this slide, to be honest, because we've just barely scratched the surface, right? But you guys know enough now to go out and read stuff and say, okay, layers, K input, yeah, dropout, okay, I got you, right? I can read the paper now at least, right? And they're generative adversarial networks. The networks work together and yet fight each other at the same time. They're really cool. No, they're used for it's weird. They take photos, feed them to these networks, and then get the other network to take that and generate new photos. And you look at them and you say, wow, that's pretty. And then you're trying to figure out what it is. And it's not anything, but it looks real. It's weird. It's real. It's hard to describe. It's totally realistic, artificially created pictures. And you look at them and go, that's... it's right, but I don't know what it is. It's really convincing. It's awesome. And the one fun thing with the recurrent neural networks is that they can use it to generate text, of course. You can train them on, say, the complete works of Shakespeare, and then feed it a seed, and then it starts spitting out Shakespeare. It's really fun. Because it looks and reads and feels like Shakespeare, but it's totally nonsensical, right? They've even done it with the Linux kernel. They took the whole Linux kernel and fed it into this network and then said, give me code, and it starts spitting out code. And it's awesome. It's perfectly indented, and it's got comments, and they're totally nonsensical, but it looks like code. And then you try to compile it, and it doesn't run because generally the problem is that it's using variables that haven't been defined, which is a problem in C, but the memory just wasn't long enough, right? But you look at it and you're like, look, there are pointers and declarations and nonsensical comments, and it's brilliant. Anyway, what else? Okay, some links. If you're interested in looking up more stuff, here are some good links. Backpropagation, if you're interested. More neural network classes. There's a teacher in CS who gave a class last year, Professor Fiedler. She gave a class on this, image analysis in neural networks in particular. Some of her material was there. Yeah, the Stanford class is also on a very similar topic. They all go into different levels of detail and different emphasis, but if you want more, there's that. And that's what I've got. So if there are any questions, or we good, or we're tired? All right, in that case, we're good. Thank you, guys. Well done.